Hello, this is Christina Long and this is the Science 411. Today's video is over chemical equilibrium. It's part 2 of a series that we started yesterday. Equilibrium is dealing with reversible reactions, and most chemical reactions are able to proceed in both directions under the appropriate conditions. An example would be this equation right here. Now, the biggest thing that you need to understand when you're dealing with equilibrium is that you're going to be dealing with an arrow that looks like that. And in some cases you'll see it written that way as well, but it depends on the typeset of what you're looking at, and if it's somebody's handwriting, it's normally going to be in that format. But that's going to tell you that you're dealing with an equilibrium or reversible reaction. So what that means is that the reaction is moving from the left to the right and then from the right to the left all at the same time. In a closed system, as products are produced, they'll react in the reverse reaction until the rates of the forward and reverse reactions are equal. Now that's pretty important, okay? So they are going to produce products until it hits an equilibrium, and then it moves backwards and forwards. So your forward rate is equal to your reverse rate at that point. And then when you reach that point, it's called chemical equilibrium. Equilibrium is a dynamic condition where rates of opposing processes are equal. So it's going to change constantly. There are 3 types of equilibrium. You've got phase equilibrium, solution equilibrium, and then chemical equilibrium. Phase equilibrium is the rate of one phase change is equal to the rate of an opposing phase change. So an example would be when 2 phases exist at the same temperature, like melting and freezing. So if it's an endothermic process, it's in the process of melting, it's going to have both solid and liquid there. So technically the rate of melting is equal to the rate of freezing. So you've got your solid and your liquid there. The second one is solution equilibrium, and that's the rate of dissolving equals the rate of crystallization. And it occurs in saturated solutions. Now, you probably are going to need a terminology review, and there are five terms here that I'd really like you to pay attention to. The first set is going to be down at the bottom here, and that's creating a solution. So you've got a solute, which is the thing that gets dissolved, and it gets put into the solvent, and then together it makes the solution. So the thing that gets dissolved is the solute, the thing that does the dissolving is the solvent, and the two of them together is going to make the solution. Now once you have solutions, well, then you've got to be able to describe them as unsaturated, saturated, or supersaturated. So you've got 2 pictures there that hopefully help paint the picture. An unsaturated solution can dissolve more solute. It doesn't have all that it can dissolve. A saturated solution means that it's dissolved all the solute it can. It's completely full. And then supersaturated is it's actually got more solute than it can actually handle, and so it ends up growing or building crystals at the bottom. So in each of those cases, you're dealing with a solution which is made up of a solute and a solvent. And again, the solute gets dissolved and the solvent does the dissolving. Now with chemical equilibrium, your third type, you're dealing with the rate of forward reaction equals the rate of your reverse reaction. Concentration of reactants and products are constant, but not necessarily equal. So your reactants and products, you're looking for your constant level. It doesn't have to be equal. So how do I know when it's hit equilibrium? Well, it's hit equilibrium. These 2 processes essentially, well, I did it a little bit early. It's going to hit right there because it's all the same. Okay, when it flatlines, that's the portion where it's talking about equilibrium. It doesn't have to be the same, but it does have to be constant. And when you're dealing with constant, you're talking about no slope. The concept of equilibrium: as the system approaches equilibrium, both forward and reverse reactions are occurring, and at equilibrium the forward and reverse reactions are proceeding at the same rate. So they're both moving, they're both going at the same rate. And again, you're talking about flat line data. Now there's something called Le Chatelier's principle, and I can't say his name, but that is what it is. Whenever stress is applied to a reaction at equilibrium, the reaction will shift its point of equilibrium to offset the stress. Stresses include temperature, pressure, changes in reactant or product, concentrations. Now, there's something called the Haber process, and it's a process basically to industrially create ammonia. And that's what that process is. And it's one of the first industrial chemical processes that came around, and it's been researched extensively. So when you're looking at these, you've got, 8 different scenarios. So by looking at these, you'd have to say which way is it going to shift equilibrium, which way is it going to move the reaction. So you've got increasing the nitrogen concentration, decreasing hydrogen, increasing ammonia, decreasing ammonia, increasing pressure, decreasing pressure, increasing temperature, decreasing temperature. So you have to look at all of those. Those are all things that you can use that act as stressors that may change things. So when we're doing this, we're going to look at these individually. So if I increase my nitrogen, what that's going to do is it's going to shift everything to the right. All right. Then I look at my next scenario. I'm going to decrease my hydrogen, so I'm going to lower that, which means that it's going to shift everything to the left. Because again, all it's trying to do is create equilibrium. It's trying to come back to balance. If I increase my ammonia, it's going to shift things to the left. If I decrease my ammonia, well, it's going to shift things to the right. Then if I increase the pressure, then what I'm looking at is I'm going to push it to the right. And if I decrease the pressure, it's going to push it to the left. And if I increase the temperature, it's actually going to move it to the left. And if I decrease it, it's going to move it to the right. All right. So again, it's got it written out for you, but it's going to shift towards the right, left, left, right, right, left, left, and then right. So, it's important that you be able to answer those for yourself. Now, equilibrium shifts due to stress. Concentration increase shifts away from the increase. So if you make an increase on the left, it's going to shift it to the right. If you increase it on the right, it's going to shift it to the left. Concentration decrease shifts towards the decrease because again, it's just trying to create equilibrium. So if you take something away, it's going to speed up and try and fill in the hole. Increase in pressure shifts in the direction of fewer gas molecules, and decrease shifts in the direction of more gas molecules. Increase in temperature favors endothermic reaction, and it shifts away from the heat. And then decrease in temperature favors exothermic reaction, and it shifts towards the heat. Now, there's the catalyst again. An addition of a catalyst changes the rate of both the forward and the reverse reactions. It doesn't favor one over the other. So there's no change in concentration, but equilibrium is reached more rapidly. So again, it's not favoring the forward or the reverse. It's just speeding everything up so it can hit equilibrium more quickly. Reactions that go to completion. Equilibrium is not reached if one of the products is withdrawn as quickly as it's produced and no new reactants are added. Basically, it's just going to run out of stuff. The reaction will continue until reactants are used up. If products are going to be removed in this process if gases are in a liquid solution, so they're going to bubble out, or if insoluble products called precipitates are created. So, those are the general notes over equilibrium. It's important that you understand the Haber process and what is going to happen to an equilibrium reaction when you add stresses to it. Between now and the end of spring break, please make sure that you've gone through and you have looked through all your notes and everything else, and you've completed the processes in Canvas up until this point. Then after spring break, we will begin writing equilibrium expressions and adding them together and doing ice charts. So, I hope everybody has a great day. Thanks for joining me, and until then, I'll have a great time. Bye.